This conference is brought to you by CallStack, a total software engineering consultancy.
Hello, everybody. It's amazing to be here yet again for the third time, talking about our work on Hermes and static Hermes. It has also been great to feel how supportive everybody here is of the project. As has already been said, my name is Tzvetan Mikov, and I'm on the Hermes team at Meta. I actually have an admission to make about this talk. This talk was supposed to be about something completely different than it actually is now. It was supposed to be about JSI and native state and host object. I know that Mark is excited about that. But we've been working on something completely new for the last few months, and we just couldn't wait to show it to you. So that's why I'm really grateful to CallStack, to organizers, that they allowed us to delay the announcement of our talk. So we wanted to be sure that we can present to you something that is actually working. And fortunately, it is, as of last week. So that's good. It's brand new. So this was very hastily prepared. I hope that you folks will have my back, because this is a long talk, and also you need your coffee. And believe it or not, it's probably even more technical than the previous ones. I know that's hard to believe. All right. So this was already asked by how many people watched or remember our talk from last year? Okay, that's a lot of hands. Actually, I see somebody back there that did not raise their hand. Security? This is not this kind of conference? Okay, you may stay. It's fine. Anyways, I hope you remember poor old John Native, that he was hitting a wall with interpreter performance in his app. And he was not happy at all, even though he's clearly AI generated. And how do you think he's doing now, after 1 year? Probably not great. We haven't released static Hermes yet. But I'm happy to say that we may have some good news for it, for him. Don't get too excited, though. We are not releasing static Hermes. It's something else. So before I announce what it is, let's take a little walk down memory lane. What makes Hermes and static Hermes special and different from other JS engines? What gives us the right to present to you guys here, to such a great audience? So as you know, Hermes is the default engine for React Native. And since its inception in 2016, boy, that feels a long time ago, it was designed and optimized for mobile usage, to run on device with very low resource consumption. And specifically and particularly, our biggest strength is the very fast startup. Now let's examine how we achieve that by contrasting Hermes with a typical web JS engine. And some of you may remember this slide from 5 years ago, or maybe not. Anyway, this is a typical web JS engine. And this slide is split in two parts. On the left part, we have build time. On the right part, we have runtime. And as you can see, almost everything is on the right part. Almost everything happens at runtime on the device of your customers, your users. We have parsing, we have compilation, we have executions, and perhaps the most interesting aspect of a modern web JS engine is the speculative nature of the execution. Because JS is so dynamic, and there isn't enough information from the source to the engine has to make a certain set of assumptions in order to execute the code fast. If and when these assumptions are violated, then it has to throw away all the work that it has done and make a new set of assumptions and run the code again with a different set. This process repeats until the right set of assumptions is hopefully found. Sometimes it is never found. But this is a complex, expensive, and unpredictable process. Now, modern JS engines are brilliant products of engineering. We at the Hermes team really admire and respect web engines. However, we believe that for some use cases, a different approach works better. Here we see how, by contrast, in Hermes, almost everything is happening on the left side of the diagram. Everything is happening at build time. Parsing, compilation, optimization. We are finally emitting a bytecode file, and that is what's executed and loaded at runtime. So loading the bytecode file requires almost no work. The entire file isn't even read into memory all at once. And most of it is read only when it's executed. That means that we are really fast to start up, and also means that our startup time does not depend on the size of the input bundle. So Hermes just does the very minimum of work lazily at the last moment when it's needed. In that way, it's very similar to the Hermes team. That's how we operate. That's how this talk was created. This is not new, by the way, but I also realize that not everybody is as familiar with Hermes as we are, and not everyone has seen our talk from 5 years ago. So what are the key features? What are the takeaways here? Hermes does ahead-of-time compilation to bytecode instead of at runtime. This compilation happens only once, and not on your user's devices. This allows us to have a very low footprint in both startup time and memory. Now, this is where things start to get interesting. How does static Hermes enter into this picture? Static Hermes builds upon Hermes. It is fundamentally an extension of Hermes which understands type annotations. Understanding types allows static Hermes to achieve performance comparable to C++, without the complexity associated with high-performance web.js engines. Remember how the web.js engines had to guess the types repeatedly, speculate, run again until they get it right? With static Hermes, we are kind of cheating. We know the types from the start because the users have given them to us. And by using these types early, we're eliminating the cost and complexity later. So armed with this information, static Hermes can emit either typed bytecode or native machine code. This has been kind of perhaps a little bit a misunderstanding of what static Hermes is. It is not only a native compiler, it is primarily a typed compiler for native or bytecodes. Now, to give you some idea of the lengths that static Hermes goes in order to optimize your code, here is a diagram of our pipeline. It is deliberately using small fonts. It is just created to impress, not to convey information. But what should stand out to you is the last 2 rows of the pipeline. One of the rows is for bytecode, one of the rows is for native code. So you see they're equivalent, they're in parallel, equally supported and maintained. Now, if static Hermes is so great, and it is, I promise, I'll ask the question that is on everybody's mind. Why haven't we released it yet? So believe it or not, there are challenges that are not fully under our control, which have prevented us from releasing it so far. I mean, static Hermes is available on GitHub. Anybody can try it, report bugs and so on, but we can't make it the default for React Native yet. Why? The main problem is that existing JS build pipelines erase type annotations. People don't usually think about that, but by the time that the JS source gets to static Hermes, it has undergone this extensive pipeline of Babel passes, packagers, and whatnot, and all of the type annotations are gone. And there's nothing that static Hermes can do about it. Now, in benchmarks and examples, we can set it up so we can consume the original annotated source code. But in practice, nobody ships their React Native app like that today. So this is a practical challenge that we need to solve. We have ideas, perhaps doing it incrementally and so on, but I hope you can see why this is not entirely trivial to do. Another complexity, another logistical complexity of native code is over-the-air updates. If you compile your app to native, then you cannot update it over the air as easily or at all. And I know people love to update their apps over the air. It's very convenient. The final problem is that a lot of untyped code still exists. Amdahl's law states that the performance of a system is limited by untyped JavaScript. Actually, that's not what it says. It says it's limited by its slowest part, which is the same thing. But this means that we must acknowledge the reality that untyped code exists, and it must be executed fast too. And our entire plan of performance cannot be based only on adding types. So with this in mind, I'm finally really excited to introduce our solution and what the Hermes team has been working on like crazy lately, bytecode translation on device. What does it mean? As we have covered before, I remember John Native, interpreters can be fast, but they have overhead. And they have inescapable fundamental performance limitations. They need to decode every instruction, dispatch to the handler of the instruction, decode the operands, and so on. And all of this adds time. Bytecode translation on device eliminates this overhead by very cheaply translating bytecode instructions to machine instructions at runtime. This means that you can continue to ship bytecode like you do today, enjoy the benefits of over-the-air updates, while simultaneously getting better performance. This unlocks better untyped performance, and it unlocks even better, I would say excellent, typed performance. So this helps your untyped JS code, but it helps static Hermes even more, because that has been our plan all along. Now, wait a minute. Translating bytecode instructions to machine instructions on device, that's a JIT, right? A just-in-time compiler. Well, yes, technically yes. This is a JIT. It compiles bytecode instructions to native instructions just in time and executes them. So now Hermes has a JIT. But in the JavaScript world, the term JIT is commonly understood to mean something more. It's usually taken to refer to the speculative execution that we talked about already, with all of its complexity. By contrast, our implementation is extremely simple because it is designed to benefit from the advanced compiler that we have and all of the optimizations that we do ahead of time. It is actually extremely simple. It does very little at runtime. So in order to avoid confusion, we decided to not call it JIT, to call it something else, even though it is technically a JIT. Now remember our original pipeline that I showed you? The bytecode translation is just one box, which proves without any doubt that it's very simple. Otherwise, it would be more boxes. But truthfully, it is really simple, and we have just found a way to make the bytecode faster, sometimes much faster, without adding much complexity. We are really happy about it. After all this talk, let's see some results. Now, I want to prepare you for the results. They may be underwhelming, but first I'll show you some untyped JS code, where we will see some useful but moderate improvements. Then I'll show you a couple of results with typed JavaScript, where static Hermes is compiling to type bytecode, and then we're executing the typed bytecode with the translator. And here we go. On this chart, we see several typical Octane benchmarks. Box2D, Crypto, Game Boy, Navier-Stokes, Richards, whatever. And they all have improved by about 50%. Thank you, thank you. Which means that if something executes for 1.5 seconds before, now it's 1 second. This is not bad. It is pretty good improvement. At the end of the chart, I've added also our two benchmarks, Body and the TypeScript ray tracer. They also increased by a good margin, so we are very happy about that. Now we can look at typed performance. This is again for the ray tracer and for Body. If any of you guys saw our chain React talk, there we covered in detail the optimizations we did for this ray tracer in static Hermes. So we have, for each benchmark, we have 4 columns. The leftmost column is I was checking whether we are out of time. OK. The leftmost column is the original Hermes. The next column is running this same untyped bytecode with our bytecode translator. And then the next column is bytecode translation with typed bytecode. And as you can see, the ray tracer is 9 times faster. So the left axis is not percent, it's times. The ray tracer is 9 times faster, even though it's still running from bytecode. The last column is the native code, which is static Hermes compiling to native. That is even faster. But as you can see, the difference is not so great. And perhaps in many cases, you don't have to resort to full native compilation. Now, this is all a little dry, so I wanted to give you a more visual and geeky example and also a sense of how fun it is to experiment with this. I literally asked ChatGPT to generate a JS program for ASCII rendering of a Mandelbrot set. It happily obliged. You can see the code on my GitHub. This is what the rendering looks like. It's animated. And the next slide is running this program with original Hermes from 2023 and with this. Yeah, honestly, I was surprised it was so much faster because this is untyped code. This is literally just something that ChatGPT spit out. Sometimes things get faster than we expect. OK, now, I actually don't think we have enough time to go through all of my assembly slides. You guys are lucky. But this will be a brief tutorial on how we actually did this and what it is like to build a JIT for Hermes. But seriously, do not do this. So first, really quickly, this is an example of what bytecode Hermes produces from JavaScript. On the left, we have very simple JavaScript source. It reads a property, multiplies it by 100, subtracts 1. And this is the corresponding byte instructions. Loading the property, multiplying it by 100, subtracting 1. As you can see the instructions. Load 1, subtract it, and so on. Now, our first attempt at the JIT was to replace all of these instructions with function calls. And this is the ARM64 assembly that I promised. All of these are function calls. The first function call loads the parameter. The second one gets the property. The third one multiplies. And these are slow. It turns out that when we did this, we did not get almost any performance improvement, shockingly. We were kind of stuck. And we figured that perhaps we can do better by considering that in JavaScript, even though you can do everything, the most common things that you usually do are fast and simple, and the rest of the things are complicated and slow. So you could multiply 2 numbers. That's easy. But JavaScript, of course, allows you to multiply a string by an array. And by having to support that, you add a lot of complexity to your JIT. So by splitting this, the code into two parts. A slow part, a slow and expensive part that executes rarely and handles all the complex cases, and a fast path that handles the fast cases. We actually were able to improve the performance significantly for untyped code. This is what it looks like for the multiply instruction. First, we have the check, which checks is the input a number. In this particular case, we already know that the other input is a number, so we only check one of it. If it is not a number, it branches down to the slow path, which does the slow call. But if it is a number, it just performs a very fast multiplication. So if you look at what the final code looks like for our example, it's just straight call ARM64 assembly. There's no calls. So this is pretty fast. Not as fast as it can be, because it still has to deal with the possibility that the type is something different, but still pretty good. Static Hermes builds on top of this because it understands type annotations. So it can emit bytecode instructions that know the types of their operands. And I'll just skip over these because this is not so important and we are almost out of time. But here is the bytecode instructions emitted for the same input by static Hermes, and this is the assembly that our JIT produces for them. As you can see, there's practically no overhead. It's just one-to-one assembly instructions matching to bytecode instructions. So this produces performance that is close, if not the same as static Hermes' native backend. Whew, this is good. I'm happy that I was able to go through all of the assembly so quickly. What are the takeaways? We have moderate speedups for untyped code. That can be used for existing code, NPM modules, and so forth. We have great speedups for static types, which React Native will probably initially use for framework, hot code. That might be one way we can ship it. And developers will optionally use types to speed up non-framework code. You might ask, okay, this is great, but when? This question has been asked a lot. When will all of this be enabled in React Native by default? As usual, everything is on GitHub already, but at Meta, we follow a process where we release to React Native only after we have tested things internally extensively. Again, anybody can use it already, but we don't feel confident to enable it by default. So in order of things that will happen sooner versus later, this is what we expect to release. First, we're going to release the beta language support that we've been working on for a long time. Classes. Somebody asked me about async iterators. 7 minutes? Wow. Well, I'm at the end, so. No, this is good. Then, fairly soon, we'll release bytecode translation because it is truly transparent. It doesn't require any changes. It's just a faster interpreter. And then when we are able to wrestle over the pipelines erasing our static types, that's when we'll release the static types compiler by default. Yeah, this is it. As usual, you can see the source on GitHub. And the slides will be published very soon, perhaps right away, so you can enjoy the assembly.